Hello, everyone. Welcome to the new week of TAF. I'm Jie, assistant professor in the Web Information Systems group at TU Delft. Nice to see you again and welcome the new audience. So, like usual, let me first give a very short recap about the topic, human-centered AI, which is a broad topic that studies the design, development, but also the use and governance of AI systems for the ultimate goal of supporting human activities in a reliable, safe, and trustworthy manner. So the topic requires research and innovation in a wide range of disciplines, including but not limited to computer science, human factors, ethics, philosophy, psychology, and etc. So in this series, we focus on the knowledge and language aspects of AI, human-centered AI, which are key concerns in making AI systems and humans understand each other and acting upon such understanding through interaction. Now, on these topics, we have invited a list of speakers whose work has made foundational contribution to these fields. So this week, I'm thrilled to introduce our new speaker, Luc De Raedt, full professor at the Department of Computer Science, KU Leuven, and director of Leuven.ai, the newly founded KU Leuven Institute for AI. He's a guest professor at Örebro University in the Wallenberg AI, Autonomous Systems and Software program. He received his PhD in computer science from KU Leuven and was full professor and chair of machine learning at Albert Ludwig University, Freiburg, Germany. His research interests are in artificial intelligence, machine learning, and data mining, as well as their applications. He's well known for his contributions in the area of learning and reasoning, in particular for his work on probabilistic and inductive programming. He co-chaired important conferences such as ECML PKDD 2001 and ICML 2005, ECAI 2012, and EJK ECAI in 2022. He's on the editorial board of Artificial Intelligence, Machine Learning, and the Journal of Machine Learning Research. He's a fellow of European Association of AI, Triple AI, and EJK trustee, and received an ERC Advanced Grant in 2015. Today, Luc will introduce his work on statistical, relational, and neuro-symbolic AI. So all participants, feel free to ask questions, but in the chat during the presentation. And after the presentation, you can unmute yourself for questions. Now, without further ado, let's welcome Professor Luc De Raedt. Thanks a lot, Luc, for being here. The floor is yours.
Okay. Thanks for the kind invitation and the kind words of introduction. So I'm going to talk about the connections between statistical relational AI and neuro-symbolic computation. Of course, this is not just my work, it's work with a lot of people. Your own Sebastian Dumanchitz, who's in the audience, I see. And then, of course, Robin, Angelica, Giuseppe, Thomas, and Thomas. So the kind of starting point for a lot of research on learning and reasoning is the book of Daniel Kahneman, Thinking Fast and Slow, that's often shown. And they distinguish like two systems. System one for thinking fast, which can do things like recognize people. You know, you don't have to think about who is who. If you just see some people in a picture, you directly can infer that. But if you do some kind of planning or solving mathematical exercises or writing a paper, then you think slow because you really need to plan ahead and there's multiple steps of inference to go through. The system one, system two division is coming back under many alternative terms. People use the data versus the knowledge-driven approach. Some people like Hector Gevner prefer solvers versus learners. Others talk about symbolic versus sub-symbolic. And there's various terms that, in a sense, all refer to similar distinctions, although there are sometimes little nuances between the two. Today, there is a lot of interest in integrating learning and reasoning, motivated by that cognitive perspective, but also because it's viewed as like, you know, the next wave in AI that's coming up. There's a lot of debate in the AI community. People agree that integrating learning and reasoning is the problem, but people don't agree as to how to do that. And there is like kind of debates about that between Benjo, LeCun, and then also on the other side, Marcus, Darwich, Tenenbaum, Geffner, and so on, basically. So it's something that is really alive and attracting a lot of attention. It's also important from a practical perspective. I mean, if you talk about self-driving cars, well, this is the kind of exam questions that we as humans need to be able to answer in order to get our license. And of course, if we talk about self-driving cars, they should be able to make similar decisions. And the kind of decisions to make here is, of course, well, infer where all the objects, say the cars, the traffic signs, the pedestrians, and so on are, and then interpret where the car you're driving is in, and the rules of traffic to make a decision as to decide who can go first, basically. And that requires perception, but it also requires correct interpretation of the context and the reasoning with the rules of traffic to be able to make that kind of distinction. If you look at the literature and the state of the art in the field, then there is this neural paradigm, which is kind of the dominant paradigm today. It's widely debated in the literature. Its applications are widely debated in the media, and it has reached amazing levels of expertise. And think about the large language models, and it's clearly sinking fast, because once you've got the model, everything goes pretty fast in a sense. But also in terms of reasoning, there is been a lot of progress onto the two main paradigms, I would say, for reasoning, which is logic on the one hand and probability on the other. And furthermore, there's been a lot of progress in integrating these two paradigms. And so people like Sebastian Dumanchitz and our group, we've been working on like integrating this these two frameworks in the field of statistical relational AI, or probabilistic logics, or probabilistic programs. And furthermore, we've also looked at learning in this. There is the quest set out for the ultimate master algorithm in machine learning and AI. That's the algorithm that will unify 5 different schools of machine learning. And what we are interested in here today is merging this 3 paradigms: logic, probability, and neural. Domingos describes 2 more, which we will not talk about. One is the analogizers, and the other is evolutionary computation, which are perhaps less about the representations that are being used than the others. So I'm gonna talk about integrating these 3 paradigms, and I'm interested in neurosymbolic computation, which is basically marrying logic and neural networks. And if you look at the first message that I'm gonna bring, then I'm basically gonna argue that this field of neurosymbolic and the field of probabilistic logics, star AI, that they actually share a lot of similar problems, and that therefore there's a lot of analogies and parallels to be drawn between the 2 fields, and that things that apply to one can actually be ported to the other part. And we've got an overview paper at this about this at the HKI 20, and there's also like a longer version out there on archive that's been under submission. I should stress that this does not cover necessarily all of neurosymbolic, because in some people use the word symbols. They would say words are symbols, and then they would talk about neuro-symbolic methods that are using words, but we use it in a stricter sense. It should be some kind of logic based formalism. And what you see if you look at the state of the art is that most of these neurosymbolic systems, that they take logic, they take knowledge, and they kind of put it, inject it, transform it into the neural network, and then the neural network is supposed to do the rest. But the downside is that you start with 2 original representations, and one is reduced to the other. And so in a sense, you lose a lot of the natural power of logic if you follow that perspective. Things that you lose is like the ability to provide explanations, to inspect, to trust the way that reasoning is going, and also like to trust the reasoning steps is also something that is kind of lost. And therefore, in the second part of the talk, I'll propose a different approach. I'll argue that if you combine two different fields like logic and neural networks, that you should get the originals as special case, and all the abilities of that you should actually retain as special cases. And in that regard, you get 1 + 1 that should equal 3, because the combined system should allow you to do more than the individual than its constituents, so to say. And that's what I'm going to illustrate with part 2 of the talk, which will be illustrating our deep probabilistic logics, deep problog and deep stocklog. But let me start with the beginning, going from starry-eye to neurosymbolic. And we've analyzed the state of the art along about 7 different dimensions. And it turns out that there is a basic distinction that is very insightful, and that actually allows you to draw the distinction between 2 categories of logic, 2 uses of graphical models, and 2 uses of neurosymbolic methods. So we'll be using mostly the logic programming paradigm and build on that, because it's very convenient. I mean, logic programs give you a toolbox and you take what you need for that. And so the kind of programs that we will be using are indicated here. This is like you've got facts like burglary and earthquake and Mary hearing the alarms. I mean, these are things that are supposed to be true. And then you also have like rules that say, for instance, Mary calls if the alarm goes off and Mary hears the alarm. And so that's like a rule in logic programs, in Prolog, that you can use. And once you have these, you can actually see that you can build proofs with that. And the proof theoretic perspective is actually the first perspective in this kind of dichotomy that spans logic, probabilistic logics, and neurosymbolic logics. And here you see proofs. We want to prove, for instance, that Mary calls, and you can actually go through a procedure. Well, Mary will call if, according to our first rule, the alarm goes off and she hears the alarm. And so you can kind of then see that you can build a proof tree, and then you can kind of apply resolution, as they call it, and kind of unfold repeatedly. I don't know whether you can see can you see the arrow on my screen or not?
We can see that.
You can see it. Okay.
Yeah.
Yes. Okay. So, well, here is this this rule, and so you can take that query that you want to prove, and with that rule, you can see, well, it's going to be true if these conditions are true, and so you can kind of apply resolution, and to prove that, well, it suffices that we prove this. Then you have alarm. There's 2 rules, and the first rule goes from alarm to earthquake. And so to prove alarm, we prove earthquake, and alternatively, we prove burglary. And so you can take this number of steps, and at the end of the day, you'll end up with a proof, because here nothing else is left to be true, to be proved. And so we can conclude that Mary calls follows from that theory. And that's kind of the first perspective on logic. It's like really this proof theoretic perspective. You start with rules and you chain backward or forward in order to draw conclusions. The second perspective is more that of logic as constraints. What you have also in SAT solvers and variations thereof, you have a set of constraints, like the one that you have here. Mary calls if and only if she hears the alarm and the alarm goes off. And then what you want to do in this kind of constraint perspective is you want to come up with possible walls, and these possible walls are assignments of truth values to the atoms, the propositions that we have in there. Like here, burglary is true. John hears the alarm is true, John calls, and all the other facts are supposed to be false. And in this possible world, well, this possible world is actually satisfying these rules, because whenever one of these conditions is true, also the conclusion part is getting true. So for instance, calls John is true in our world, and also the other combination John hears the alarm and alarm, they're also true in that possible world. And so that shows that this possible world satisfies this kind of set of constraint, this constraint, and that therefore it is a model of the theory. And that's like the model theoretic perspective that we follow here. And so you have like this two frameworks. You have on the one hand this directed prologue proof-based kind of approach, and on the other hand you have like these kind of constraints, and that comes back in probabilistic graphical models. You can easily see that, and I'll show that this kind of annotated prologues, that they will be able to represent Bayesian networks. And you'll also see that Markov logic is nothing else than making these constraints, the satisfiability perspective, to soften that, because what you get in Markov logic is logical statements, and they carry weights, and the higher the weight, the more important the constraint is. In the worst case, it's kind of infinite, and that would mean it's a hard constraint, just like a logical one that must be satisfied in order for a world to be possible, to be a model of the theory. But unlike pure logic, if a possible world violates one of these constraints, well, the possible world becomes not impossible. It's just that it will have a much lower probability, the probability being described by what we have here. And so that also maps onto undirected graphical models, the kind of Markov networks that from which Markov logic borrows its name in a sense. Now that's for probabilistic graphical models. If we go one step further to neuro-symbolic systems, the neuro-symbolic AI, then we again will see that these two types of logic come back. On the one hand, you have logic that's used as a kind of neural program, and on the other hand, there is logic that's used as soft constraints to, in a sense, regularize the neural networks. And that's kind of reminiscent of the star AI approaches. So let me go back to one of the earliest approaches, probably the earliest neuro-symbolic AI approach, which is due to Towle and Shavlik almost 30 years ago. Their K-band system was starting from these prologue programs, and it was like also this propositional prologue programs that they would then kind of rewrite into a representation of all proofs, and that is what you see here. This is a so-called AND OR tree. I mean, A is true if B and Z are true. And then, well, to prove B, well, we have like two of these rules. We can go here or we can go there. And so you've got an AND OR tree. And that would be the basis for the neural network, because once they've constructed the AND OR tree, what they would try to do is they would learn how to predict A from the leaves of the tree, in a sense. And the way that they would do that is then turn that AND OR tree into a neural network. They would perhaps introduce a couple of extra nodes at different layers, and they would introduce a lot of extra weights at a kind of typically fully connected from layer to layer neural network. And they would then train that neural network using backprop, using the usual technology that we all know so well. And then to see how visionary they were after learning this, they would try to reconstruct the rules, the learned rules, so to say, from the neural network. And that's kind of probably the earliest approach to kind of providing explanations in these neural networks. So also that is something that they kind of pioneered in some follow-up work, in a sense. The exact details of how they work is perhaps less important, but the spirit of their work is still very, very much alive, because other people, like, to give one example of the group around Andrej Kozelka in Prague, is doing something related in their lifted relational neural networks. They would have like prologue rules. They would annotate them with a kind of fuzzy operations and all that. They would produce proof trees, and they would turn that into neural networks that are then used for training. a system that I fancy a lot and that I think is pretty nice. And also, if I got it right, is very relevant for G's purposes, is the neural tier improver. Because what you have there is, again, the idea that you build proof trees and you turn the proof trees into neural networks. But here you will build proof trees starting from these rules. And unlike real logic, which is hard, and which required, hard matching between a rule and something you want to prove. Like here, you've got the rule for grandfather of, and here you want to prove that Abe is the grandpa of Bart. So grandfather of, grandpa of. If you work with pure logic, hard logic, this does not match, this does not unify, and so the proof would fail. In the NTP, the nice thing is that they produce this kind of soft matching by looking into embedding space and are still able to come up with a kind of structure which is then fine-tuned to learn the embeddings and to learn all the parameters and all that. And there's been a couple of papers on that actually. In most cases, however, the logic is kind of, encoded in the neural network. And once that's done, there's no way that you can still reason logically. All that ability is gone in a sense. And that is why we will propose a different type of approach, which will have a much tighter integration between the logic and the neural approaches. So this was like the left part. It's the neural program. It's very much in the spirit of directed graphical models of this model-based perspective. Let's now look at the constraint-based perspective, where there's an example from a paper by the team around Guy van den Broek at UCLA, which again is very beautiful and it's very nice. What they have is like, this is an example that they give to illustrate their semantic loss, as it is called. There is like the input layer of the neural network. Here you're trying to do multi-class classification. And if you come up with these values at the output nodes, like 0.8, 0.3, 0.9, then you're probably not very happy. Of course, you could do a soft, you could do a soft max, but suppose you don't do that, because then you have the difficulty in like predicting, is it the P1 or is it the P3? And basically something happens here that you don't want. There is like two of these outputs that end up with high values. And what you would actually want to have is that only one of these outputs has a high values and the others have actually low values. If you do multi-class classification, you want to predict one class and not the others. And you can formalize that by saying, well, a constraint on the outputs should be satisfied. That constraint is logical, and that says exactly one of the outputs should be true. And that's like the kind of hard constraint. But of course, given that you work also with neural networks, you need soft constraint, you need to soften it. And so they soften it by turning that constraint into a loss function, and the loss is taking into account the probability that the constraint is satisfied. You can consider the output values here as probabilities, and then you can feed that into this expression to compute the probability that the constraint is satisfied. And if it is, well, then there is, of course, if the constraint is satisfied, there is no loss function, the loss is 0. But if it's not satisfied, you can turn that into this semantic loss function, which has some nice properties, and you can use it to regularize it, your neural network. You can combine that together with a traditional loss in the usual way to speed up. And again, that idea of using logic as a kind of constraints is taken over or reappears in many forms in the Neuro-Symbolic literature. There is the logic tensor networks by Luciano Serafini and Arthur Garcet. There is the SBR by the group around Diligenti and Gori in Siena that is doing very similar things. And again, you see that, the logic is kind of, it's in the regularizer, and it's kind of not pushed well, in the sense that the ability to reason logically on that constraint theory is lost. It's just used to penalize your neural network in a sense, and so you lose it in a sense. And that's, I would say, an undesirable property that we would like to avoid. There's further dimensions. I mean, the dimension that I was talking about was this neural programs versus the neural constraints that spans logic, probability, and neural networks. There's other distinctions you can make, like you can use pure logic as values, that's 0, 1s. You can go for probabilities, which is what we typically do, but which is computationally expensive. And you can look at fuzzy logics and start to use these. I'm not going to cover that part because it's pretty technical, and there's not that much time to do so. So let me just mention that there are these 3 ways of doing things. The pure logic, things that are true or false, the probabilistic logics, where you've got things that are true with a particular probability, like your walls will be true with a particular probability. And then what you also have is this kind of soft logics, this fuzzy logics that are being used. And in that case, you also assign a kind of value to each of the walls, to each of the statements in the walls. But in a probabilistic world, the world as such gets a particular probability, whereas here, this is kind of degree of membership. So a 0.7 burglary is not a probability of getting a burglary being 70%, but rather saying, well, at the scale of burglaries, this is a quite heavy burglary. It's not the most extreme form, but still it's like a pretty important one. And like the call of John, like 0.3 is like, oh, hey, this is, maybe the sound was not too loud. That's actually what this means. What you have to keep in mind is that people use these fuzzy variations mainly for computational reasons. It's a lot easier computationally to optimize your parameters if you work with fuzzy than if you work with the probabilistic parameters. On the other hand, you also lose quite some intuitions, like for instance, the fact that if you have, for instance, A or B or C or D as a constraint, then, well, according to some of these T-norms, as they called, that fuzzy constraint would be satisfied even if all of the values of A, B, C, and D would be pretty low, like 0.25. They would still be satisfied, so to say. Also, things like transitivity do not necessarily follow from the use of these fuzzy logics. Given that the approaches I've talked about are actually reducing the logic, they're pushing the logic inside the neural network, we propose this different approach where logic and neural networks should work side by side, and there should be a kind of bidirectional communication between the 2 layers. We talk about an interface layer. Pipelines is not what we do, because a pipeline in one direction, in an interface, you've got really flow in 2 directions, and pipelines are really for plumbers. It's not real interfaces, and here we go further than that. There is 2 types of models that I can talk about. One type of model is the one that's based on Bayesian networks and a combination with Prolog. It's based on our probabilistic programming language. The other, if you look at graphs, Prolog can be viewed as a kind of random graph model, because if you take a graph, then every edge in that graph would be in or out with a particular probability. But you can also take a random walk model, and in random walks, well, you walk differently, and that's more the semantics that also probabilistic grammars have. And also there we've made a version of this logic programs that work with that, and that's built on a framework called SLP, stochastic logic programs. And in both cases, the same method applies. we take an existing probabilistic logic, an existing probabilistic programming language, and we then inject kind of neural predicates that acts as the interface between the neural and the logical components. In both cases, you retain the full expressivity of the original language. So in this case, that means that Deep Problog is a programming language. It's a probabilistic programming language. It's also a logic programming language. And on top of that, it interfaces with neural networks. The nice thing about building on top of an existing framework is that you retain, well, the expressivity. You also retain the clear semantics in a sense. And that contrasts a little bit with many of the other systems that have been around, which either reduce the expressivity of the logic or get less clear semantics for their framework, more an operational one rather than a declarative one, so to say. So let me go in 2 steps. I'm going to go from logic, from Prolog to Problog, and then from Problog to Deep Problog, while taking this Prolog kind of perspective. So this is the example of the programming language Prolog that I just went through. It's about the burglaries and so on. And then you could build proofs. And if you want to make that probabilistic, then it's a good idea to look at the seminal work by David Poole and Taisuke Sato, who developed well this kind of framework, and also the first learning algorithm, the first probabilistic programming language with learning built in, so to say. And that was in the early 90s. What they were looking for was a way to unify the key concepts in logic and probability. And when you have to do something like that, it's always a good idea to look at the most basic, the simplest possible concepts and try to unite them, to mix them, to unify them. And in logic, that's a propositional variable. In probability theory, that's a random variable. And so if you kind of view them as being the same, then that's all you need in a sense to marry probability theory and logic. And they also then noticed that if you want to incorporate that idea into Prolog, well, the only thing that you need to do is to turn facts into probabilistic facts. And here you see that this has been done. We now have burglary that's true with a probability 10% and earthquake with probability 5% and so on. All of these facts are marginally independent of one another. I mean, this is very similar to what you have in Bayesian networks. I mean, the facts are like the nodes in a Bayesian network without any parents, so they're mutually independent. And the dependencies are introduced via the rules that actually make that you get dependencies in there in a sense. Okay, so here is this probabilistic logic program on the left, and we can now see how to adapt our proof procedure to cope with that. Here is a proof for alarm. There's 2 possibilities. We can go via burglary or via earthquake. And so we get 2 proofs, and then it's pretty tempting to say the probability of alarm is simply going to be the sum of these 2 probabilities. I mean, the probability of one proof is the product of all the probabilistic facts that you would encounter along that proof. So, but in both cases, there is only one. But that, to combine that, what you might want to do is like, it's kind of tempting to say the probability of alarm is just, it's the probability of the left or the right branch. And then it's kind of tempting to say it's the sum of these. But of course, you also have to subtract the intersection, the probability that both branches are true at the same time. And that is what causes the difficulties in the inference procedure that is at the heart of probabilistic inference. It's this what makes inference in Bayesian networks and in these probabilistic programs quite intractable. It's sharply complete. And so a lot of work in this is actually going to inference and fast inference. You can also view these probabilistic programs as kind of generative models. That's indicated here. Here you've got different rules. There you start with the empty model, the empty possible world. then okay, you know that earthquake, that must be true. So in here, we've got earthquake being true. If earthquake is true, then the alarm goes off with probability 60%. So in this node, I hope you can see this. There is earthquake and alarm true. Here there's earthquake is still there, but alarm is not in there yet because it's the other branch. And so you can kind of build up this proof tree of possible walls, where at the leaves of the tree, you will get the different possible walls. And that also defines your semantics in a kind of declarative fashion. You've got alarm. If you then want to know what the probability of alarm is, what you will do is you look at the leaves of this tree and you sum up the probabilities of these leaves where alarm occurs. That's the orange ones. And to get one of these, get the probability of the leftmost branch, you just multiply all the numbers that you encountered on the branch from the root of the tree till the leaves, and that should be something like these. That should be the second one, and so on. And this gives you like the semantics, the meaning of these programs. I guess it should be clear that this kind of programs can represent Bayesian networks. You can take this, you can directly map it on there. That's quite easy. But in addition, you get a lot of expressivity because this is a programming language. So you can do much, much more than with just Bayesian networks. And one of the things that received a lot of attention in the literature is this so-called plate notation. Here you've got these plates, 2 plates, one for students, one for courses. And there are like 2 variables, well, 2 sets of variables. There is this intelligence that's going to be a variable for every student, and difficulty for every course, and then grade for every combination of them, basically. And so if you now take students and courses, then what you will get is this kind of unrolled Bayesian network that connects multiple students to multiple courses and grades, and that you can actually do probabilistic inference in. And that's the reason why these plates are used. They kind of compact, compressed notations for a joint where you can reason over multiple entities, like the students and courses in this case. And so you get a very compact model. You can map that directly onto Problog. It's pretty easy to do that because the only thing that you need to do is every entry in a conditional probability table, you will map onto one of these rules. For instance, the red rule here is the case where the student is intelligent, the course is difficult. And in that case, there is like this possibility of probability of getting an A with 30%, a B with 50%, a C with 20%. And that's actually encoding one of the entries in the conditional probability table for grade. And then here you map, you represent the students. Well, you represent the plates for student and difficulty, and you say which students you have and which courses, and then that's gonna give your result. The nice thing about this is that you can just mix this. You can just add further logic, further ontologies on top of that, and do all the kind of reasoning that you would typically want to do. For instance, rules that say when students perform unsatisfactory or when they're excellent and that kind of thing. You can all simply add that by writing the rules down and doing inference in these logics. There's quite a number of applications of Problog. There's already old ones where we've built models of like games, like where because games are like they have like these states, and these states evolve over time. It's a bit like graph structures, and typically there will be added cities, added alliances, players, and stuff like that. And if you can build a dynamic model of that, that allows you to predict future actions of your opponents that are likely, then you can take better actions. And so we did this a couple of years ago. We've also incorporated variations of Problog that also deal with numeric, continuous numeric information in the form of continuous distributions, for instance, to point to coordinates that you need in robotics application. We've also used these to reason over that. And here are some examples to reason about occluded objects, to track as well. Here to learn actions of the effects of actions, where you're interested in, the displacement of something if you tap it or push it. And then you can use this to do planning, try to configure objects in a particular configuration on a shelf. That is then what was used later. We've done stuff in biological applications. And if you want to try it out, you can check here. Just search for Problog, and there's a pretty nice tutorial and interface where you can try it out yourself and cope with that. So that's the probabilistic logic part. Let's now extend it with this neural networks. And so in these neural networks, when we were first discussing this, we were trying to come up with an idea that would be similar to that of Sato and Poole. I mean, we were looking for a simple combination of logic and neural networks where the two would kind of match. And we were also looking at the simple task of classifying MNIST images. And if you look at the classification of an MNIST image, then you get like these numbers between 0 and 1. If I see numbers between 0 and 1 that predict, a kind of and that sum to 1, then I view them as kind of probabilities, even though they are not. And so we said, well, let's turn these neural networks into neural predicates. And that provides the interface between the logic and the neural networks. And that's the only thing also that you need, in a sense, to make Problog be able to cope and work and learn with neural networks, in a sense. It's indicated here. The neural predicate is digit, and the input will be X. X will be an MNIST image. And then there is like 10 possible outputs in this example, the numbers between 0 and 9. And the neural network is here. So that's like the annotation that we use for that. The name is this MNIST network. And what it will do is actually it will map, if you feed in an MNIST image, it will compute the probabilities of these classifications. And that's very much the same kind of representation that you had in this alarm and burglary example, and this throwing at windows that would break. That's this kind of annotated disjunction, this ADs, as we call them. Here you see an example of the usage of this. We define addition of two MNIST digits, two MNIST images, and the result is then like a real number, a natural number that you want to obtain. And the definition of addition is simple. While you map X, the MNIST image, to the number and one it represents, you do the same for the second MNIST. You get that number, and then you require that the output Z is like the sum of the two. And the idea then is that if I now feed in examples, and that's the only examples I'm feeding in, of the type 2 MNIST images plus their results, if I feed that in, then this acts as a kind of constraint, because here N1 and N2, what I do know is that N1 plus N2 must be equal to 8 for this particular example. And so I can choose options like 2 plus 6, 4 plus 4, 5 plus 3, and so on, but I cannot choose 2 and 2 because that would not sum up to 8. And so that would not satisfy the constraint that this is giving. Of course, we were then carrying out tests. We had just examples at the level of addition, not at the level of digits. And we were then looking at how accurate the abduced numbers. I mean, I heard G talk about abduction. So in a sense, you abduce the numbers here and we were looking at how accurate this actually is, and we compared it also to classical neural networks, and of course it did much better because it also has more knowledge. People in neural networks wouldn't find this very impressive yet, but if you work with lists of these MNIST images, it's already a lot harder for neural networks to tackle this task. And in deep problem, the only thing that you need to do is, you assume again that you know the rules of addition. And if you know the rules of addition, you can write it down in this Prolog program. Digit is again unknown. You don't see any example for that. And again, you can see that you learn to classify the digits correctly with reasonable accuracy. You can take variations of this, like to show that it's also probabilistic. Here is a little variation where you've got this noisy parameter, this noisy fact, so to say. And with probability noisy, you output a random number between 0 and 18. With probability 1 minus noisy, not noisy, you output what you had before. And you can see that, well, standard baselines don't really work for that, but with explicitly modeling this in deep Prolog, you can actually recover the noise level, and so you can learn this probabilistic parameter in addition to learning the correct classification of the underlying digits. What was nice is that inference was actually just a simple extension of what we did in Prolog already. In Prolog, what we do is we first ground out the program with regard to a query, and then you get this kind of expressions on the left, which you kind of rewrite using some logic programming technology into these expressions. These are then compiled into these circuits. These are logical circuits, and that's knowledge compilation that is used for that. A whole nice machinery to give you circuits from which you can compute correctly various operations. And once you have the circuits, well, you change the ands into multiplications and the ors into additions, and you'll get the correct answers up there. That solves this problem, with this adding of two alternative proofs. It solves this disjoint sum problem through the compilation step. Now, the only thing to do to change into the Prolog is that, well, if you just run the machinery of Prolog, you get the circuits, and if you feed in this neural predicates, the neural predicates will end up as the leaves of the circuits, and you then have to realize that these leaves are nothing else than the neural networks, and so they are represented there. And then once you have that, it's easy to see that you have the loss function at the top, and you push down the gradient to the leaves in the probabilistic part, and then from the leaves in the neural network part, and you kind of simply adapt that. We did further experiments, a bit on rule learning, a bit on a bit on things like sorting, addition, also simple word algebra problems, a little bit with cards and predicting poker hands, whether they would win or lose, because that's also a probabilistic task. And we simulated the neural tier improver using particular ways. And so there's a lot of things you can do then. You can work with embeddings. Do I still have 5 minutes, or should I conclude?
It would be nice if you can conclude in a couple of minutes.
Okay. Okay, so let me
question answers.
Okay, so let me also simply mention the other one. I mean, what we've done in deep Prolog is we've taken a probabilistic logic and we've then injected this neural predicates, so to say, and that turns out to be a pretty general principle that you can do. You can apply that also to other frameworks, and we've applied that to grammars. These are the standard context-free grammars that you can take. You can look at probabilistic versions thereof that have a bit of a different semantics. There is unification-based grammars where you can pass on arguments and you can compute them. And then, of course, you can then have the unification-based probabilistic grammars that work. And once you have that, well, you can also inject these neural predicates that will then work at the terminal level, so to say, to parse and to learn how to parse correctly numbers. And that's actually a much faster system than the problog, because the underlying machinery for grammars is a lot more efficient than that for Bayesian networks. And you don't have to do this compilation step, so to say. But let me skip the details of that and simply conclude. There's still a lot of challenges with these systems. One of them is scaling up. The other is like looking into real-life applications. I mean, we've got a lot of real-life applications of the probabilistic logics, but we still need to port some of them. Like, I'm very interested in porting the robotics ones to dproblog and to be able to fully exploit that. And we're also looking at, for instance, dynamics, continuous distributions, and all that. And this is actually an interesting area for starting researchers. Okay, that's my conclusions. I hope I've argued that the two fields share a lot of problems and also similar solutions, and then that you really need to interface between the logic and the neural networks, not just push down the logic into the neural networks and then forget about it. So thanks.
Thank you, Luc. Thanks for introducing the work done on this important topic in a very concise language. And thanks for introducing your own amazing and foundational work. So now audiences can ask questions. You can just unmute yourself and speak. Maybe while the audience is speaking. Oh yeah, go ahead.
I was saying, like, since there's no one, I can actually go ahead and do one. My question is about the neural theorem prover. It's a quick one, because like you mentioned that that one is essentially like based on embeddings of what, like the individual like instructions in the logical program. Oh, okay. So that's how you get the soft matching.
Yes.
Okay.
Yes. So yeah, that's the way to learn the embeddings that kind of would allow soft matches and stuff like that. Yes.
Okay. They use directly those. Yeah. It was like a really simple one. But thank you.
I also have a question, but this is mostly for clarification. So, Luc, you mentioned, you introduced these two ways of neuro-symbolic merging, right? So, for the second part, I was wondering how that is different from, let's say, Markov logic, right? So, the work that you present, deeper prop logic, right? Basically, there you take the output from neural nets as, if I understand correctly, right? You take the output from that as a predicate in this the logic formulas, right?
Yes.
And then you use this prop log, which you have developed.
Yes.
And I was thinking how that relates to Markov logic. In Markov logic, we also use the logic programming on top of Markov network, right? Because all the learning happens through the Markov logic, and then the inference is done there. So
yes.
Yeah, can you maybe, this?
Yes, so like Markov logic is like, it's much more so you have like this directed and undirected graphical models. And so problog is much more in the directed spirits of the Bayesian networks. Whereas Markov logic is in the undirected space, where you have like the factors corresponding to the clicks in a sense, and every click coming from an instance of the clause, a kind of ground instance of that clause. Secondly, I mean, but also like what we've done for the prop block, people have also done for the for Markov logic. There is neural versions thereof. Like also my colleague here, Giuseppe Mara, has developed like this relational Markov logic networks and stuff like that, which is actually taking a kind of related idea. You replace, you know, they replace then the factors, so to say. They allow for neural components in there, and so again, the same machinery you can do there. Then there is also work by the group of Lise Couture, who's using this fuzzy variations of Markov logic, this probabilistic soft logic, and she's been also like injecting kind of neural predicates in their approach, and they also have a neural version. And so it turns out that this dichotomy between this kind of directed inference-based versions and the undirected, that is retained in a sense. What Markov logic is not, it's not a programming language. It doesn't have the power of a probabilistic programming language. It's kind of relational. Whereas the ones based on Bayes networks typically, well, or often have that ability. They do have that ability.
Can I see, let's say, the deep prop log as extension of this idea of logic as a constraint, or maybe not an extension, but more like to build a full you know, a full component of logic programming on top of the neural nets?
Well, it's like you have the two side by side in a sense, right? So like most of the frameworks, they kind of use the logic and then, you know, they push it down and then it's gone. And there used to be in the past, like in the old days, there used to be also approaches that would put the neural network inside the logic and then forget about the neural network. But I think you need really to have both of them. They serve different roles, and so you want to get both of them, and you also want to interface them. You want the interface to be as much as possible. Like we're very interested in working on, for instance, manipulating the embeddings in a symbolic way. So that is kind of interesting stuff to do. We're also interested in like using numeric output of the neural networks rather than just the probability, so to say. And so we're building on making that component stronger.
I see. Thanks. I actually have a follow-up question about this idea of manipulating embeddings. But maybe I should be less selfish and leave the space to the audience.
I actually have one question or two questions. First of all, thanks a lot for the talk. So my first question is, so I see this logic units you have in your whole graph, right? So I wonder, in real practice or in applications you have, usually, what is the size of this units you are dealing with? Like usually, how many of this?
The circuits can become pretty large, but scaling up to large programs is hard. So you need kind of approximate reasoning, and that's to some extent, well, to a large extent, an open question how to scale it up really to. And then what matters is the size of the circuits to get. The size of the groundings and the logic part is in a sense the limiting factor there. Because okay, I mean the neural networks have been optimized for, you know, by companies. Massive, and there's no such effort as yet by this kind of companies. And okay, in knowledge graphs, people, and I guess maybe that's something that's more popular in your group. In knowledge graphs, of course, they've also been able to scale up very heavily and very significantly. And I guess that's also a very interesting direction to combine these two technologies. And that's also what we are exploring in some projects. Yeah.
I see. All right, the second question is, so my understanding is by embedding those logics in your models, you kind of provide some reasoning or some explanations of the predictions, right? So in this case, do you think it's also, let's say, do you also think it's necessary or does it need to check the truthfulness of those explanations? Or do you think those explanations are actually definitely true, they've been correct, we don't need to test them at all?
Well, if the explanation comes from the logic itself, I think they should be reliable. But at least you can show you can in a sense show the proofs. You can also show the whole derivation, so you get in a sense explanations for free.
Yeah. So you also have the neural networks there. So my understanding is, if you only have this hard rules, sure, those reasonings is true.
Yes.
But if you have those neural models, they somehow bring up some uncertainties, right? And does that also affect your reasoning? The truth, probably it also affects a little bit of the reasoning, or not?
Well, in any case, you can still use the machinery of like probabilistic abduction. I mean, when Poole invented this kind of probabilistic logics, he was talking about probabilistic abduction. He was really like looking like what's the most likely explanation or the most likely proofs and all of that. And so all of that machinery is also something you can use. Of course, yeah, if your neural network is completely wrong, yeah, then that will, well, one part in the explanation will be wrong as well. But at least you can verify that, and yeah, and in terms of the neural theory improver, you'll also see like what it matches to in a sense, and things like that. So yeah, so you get more control naturally.
Thanks a lot.
Do we have maybe another question from the audience? Luc, how much time do you get? Looking at the clock, we are 4 minutes more than the talk. But if you can with us for one or two more minutes,
yes, that's okay. Yes,
yeah, that'd be nice. Thanks. I have one last question from my side. So I'm sure, Luc, you have been asked by other people similar questions. Like, there is always this debate between, like also you mentioned in the beginning of your talk, right? Symbolism versus connectionism, and it's a debate that can be traced back, deep in the past in philosophy, right? So, so what's your view? I'm sure, I mean, your work says something, says a lot already about your view on this debate. Like, what's the fundamental way of humans learning? But I'm curious if you have anything that you would like to share.
Well, I guess you need both approaches. Like, I mean, we have system 1, system 2. I think you need also like to embrace neural networks and the cool things it can do. But there's still a lot of limitations. If you can't, it's hard to kind of incorporate knowledge in that. It kind of needs a lot of data. Kind of, it can, like a lot of the reasoning tasks that it seems to be doing is relatively simple because it's like in situations where there's not that many possibilities so far. But solving, like, for instance, hard constraint satisfaction problems, I don't see neural networks doing that directly. Again, there's a couple of approaches that do that, but why would I use these if I have like other approaches that work well? So, and that give me guarantees and explainability, and that I know give me correct answers. So, I think the challenge is to combine the two in a sense, yeah, that's like the, at least in the short run, that should be the kind of, I mean, like in the rules of traffic, would people really want to learn the rules of traffic by just observation? I think that would not make a lot of sense to me. There are like these rules that we all know and that we use to communicate to one another and to explain things. And that's not just in traffic, but it's like in a lot of other domains as well. And you'd expect that, yeah, we can communicate about these rules and that these can be taken into account. And I think so far that's not happening. I'll never say it will never happen, but yeah, I mean, let's see.
Yeah, indeed. I fully agree that, there are all these, in real tasks, there are all these rules that we humans have accumulated over the time that we are confident that they would work, especially in traffic, for example. This is a man-built scenarios, right? On the road, how you drive. Yeah, thanks. Cool, thanks, Luc. I might have more questions, but I will follow up offline.
Okay.
So thanks again,
good.
Luc.
Okay, thanks.
It's a
Bye.
great pleasure to have you. And thanks everyone for joining the Academic Fringe Festival. Next week we will have Basmira from Microsoft introducing their efforts on responsible AI toolbox. So see you next week.
Okay, thanks. Bye.
Bye.